This is an introduction to RTOSs. An RTOS is a real-time operating system. It is typically used on microcontrollers, and it is an operating system much like Linux or Windows is an operating system, but with a real-time aspect. We'll get into more details in a moment. To begin with, let's talk about some interesting facts about RTOSs. So the Mars rover suffered from an RTOS priority inversion. The bug was a developer bug, as RTOS had a priority inversion capability, but the developer had turned it off. The developers had noticed an issue during development, but figured it was a hardware glitch. This is a good lesson learned. There is no such thing as a glitch. It's only a bug you don't understand. So Toyota had a issue. They had cars which would actually unintentionally start accelerating, and a person could not stop it. This was reported by many people, and they kept thinking it was the floor mats getting stuck on the accelerator pedal. They finally actually started looking into the problem after a California Highway Patrol officer was killed, him and his family. They were in a Lexus vehicle, and they started accelerating down the road. The police officer called 911 and discussed the problem and tried to figure out what was going on, and the car would not stop accelerating. It ended up all 4 occupants of the car were killed, and they found out later that the code was described as spaghetti code and untestable. The program code for the acceleration had over 9,273 global variables. As I've said before, global variables are evil. Task concurrency, volatile variable errors, and many other problems were in this code base. Toyota's code, this code that caused this bug, is the world's most expensive code due to the amount Toyota had to pay out for people that had been injured and killed, as well as the fines for such bad development. Now, I should also mention that this had a homegrown RTOS. So the developer wrote their own RTOS for this, and that was part of the issues identified in the review of this code. So our agenda today is discuss what is an RTOS and how it's different from a regular operating system like Windows. Why use an RTOS? What is the cost of an RTOS? What is normally included in an RTOS? Key concepts of an RTOS, and bugs of RTOSs versus bare metal. So what is an RTOS? An RTOS is a real-time operating system. Real-time means that from a task is flagged to run until it runs is bounded by a maximum time. Generally, this includes task scheduling. RTOS includes task scheduling, memory management, mutual exclusion or mutexes, and our semaphores, task-to-task communications, and hardware abstractions. Why use an RTOS? First of all, anything you can do in an RTOS, you can do without one. RTOS provides an abstraction layer which allows tasks to be developed independently. A good RTOS provides abstraction for the hardware drivers. RTOS often have faster code development because multiple developers can be working on tasks independent. So they can write their task as if they're the only one running on the processor, and thus get their task done independent of other developers. RTOS can typically have fewer bugs when implemented correctly. The RTOS is not free. It takes time away from doing other things to manage the operating system itself. It takes memory and code space to implement the RTOS. And of course, in doing so, it also often takes more battery power because it has to run more code. It also requires a shift in the mindset. So, what is the difference between RTOS, Linux, and bare metal? Linux is not real time. When you tell a task to run in Linux, you do not know when it's going to run. A lot of this is because Linux runs on a PC, and even executing code on a PC is not known. PCs typically have biases. If they have a bug in an instruction, they will generate an interrupt, which calls into a bias for a software workaround. This makes it very difficult to actually know how long code will run, even if you know the assembly instructions. And as such, most PCs are not considered real-time environments. Bare metal development is optimal use of hardware. However, it may not be optimal for the time and money it takes to develop the software to run on it. RTOS is a blend. It adds additional cost in hardware, CPU time, RAM, etc., but generally reduces development cost. So RTOS includes a scheduler. This determines when tasks, or threads if you will, should run. The scheduler can be preemptive, which means one task can interrupt another one. It can be round robin. It can be cooperative, where a task runs until it decides it does not need to run and releases the processor. RTOS typically includes mutual exclusions and semaphores. This allows code from preventing other code from running, or allows a code to prevent other code from running. So it allows atomic code operation and prevents two tasks from using the same resource, like peripheral, UR, I2C at the same time. RTOS typically includes memory management. They typically include a way to replace malloc with error checking, memory management, maybe a pool-based memory management, for example. RTOS have the concept of tasks, as we discussed. These are processes or threads. Each task typically has its own stack. The RTOS can be a tick-based RTOS or even tickless. And we'll get to that a little bit later. An RTOS allows you to run an application. The application under the covers, the RTOS basically under the covers, run multiple tasks to accomplish specific application or specific goals. Examples might be a task to run a web server, a task to run serial data logger, tasks to sample ADCs, tasks to do single processing, etc. In a desktop OS, like Windows or Linux, a program runs as a process. The process can have multiple threads, all of which can run concurrently, and usually they can also run with different priorities. In RTOS, it is common to call a process a task. Generally, a process can have multiple threads. A task contains no threads and does one thing and only one thing well. Tasks are basically small, self-contained programs. They often have their own stacks. They run as though they're the only program running on the processor. And they do one thing, and they usually do that one thing very well, if you program it very well. Scheduler. Scheduler goes through and determines which task needs to run. And it's trying to get the task to run all the time. There are different kinds of scheduling algorithms: cooperative, round robin, priority based, etc. Each of these can even be preemptive or not. A preemptive schedulers basically means a task that has a higher priority can stop a task that is currently running so that it runs. So let's discuss cooperative. Cooperative is each task runs until it thinks it's used a fair amount of time and yields to the next task. And so, it's a shared resource, like you would go to the playground, you swing on the swings for a while, then you get off and give another kid a turn. Now, a bad kid, and a bad task, could go and take all the processor time and never give anybody else any time. Round robin scheduler. This is where a task gets a fixed amount of time, and the time is predetermined and weighted for each task. This way, no task can consume all the processor. Everybody gets a specific amount of time on the swing, and then they have to get off. And so below is a picture where tasks get a specific amount of time on the processor, and then they get kicked off and another task run. Priority base. Here, a task runs based on who is the highest priority. For example, the boss would get the coffee maker first if there's a limited amount of coffee. Each task is assigned a priority. One with the highest priority wins. In this environment, if everything's a high priority, obviously the low priority may never get processor time. And basically, when we get back to where everything's a high priority, we're back to cooperative. Preemptive scheduler. The OS can kick a task off a processor at any time. Basically, this means higher priority tasks need to run. I'm bigger, I'm better, I force you off. This requires task priorities to know who gets the processor next. There's all kinds of scheduling algorithms out there. There's preemptive with minimum time, preemptive with guaranteed run every X seconds, scheduling based on resource availability. If you're really interested, you ought to look up the BFS scheduler for Linux. There's lots of others. Mutual exclusions and critical sections. What if a task is in the middle of some code and gets kicked off the processor? We need a way to prevent the RTOS, the operating system, from kicking off critical tasks that are in the middle of something that is a very high priority. For example, what if a task is currently right into an I2C memory and gets kicked off and another task needs to write to the same I2C memory? Then you have resource contention. So the correct answer here is to have a mutual exclusion that says, okay, while I'm writing to the I2C, nobody else can stop me from doing it. We will discuss priority inversion and deadlocks in another class. Memory management. This is not really required for an RTOS, but it's typically added in because it's a commonly used in RTOS. Most common form of memory management is to do what they call memory pools. The basic idea is you take your memory, your heap memory, and you allocate it into fixed sizes. And then you pool those together. So if you want 1 byte, you get a fixed size. For example, if you said your fixed size is 256 bytes, if you want 1 byte, you get 256 bytes. If you want 10 bytes, you get 256 bytes. This helps prevent the heap from getting fragmented, where you need continuous memory, because you've already decided that your continuous memory size will be a minimum of 256 bytes. A tick versus tickless RTOS. So RTOSs typically have a time tick. Specifically, the RTOS operating system has to actually run itself. And so it will often run based upon a timer. So a task is executing, the timer triggers, and it runs the RTOS to see if somebody else needs to run. It may switch tasks then. And so in this graph, we can see that task 1's running. Tick happens, RTOS runs, it says, oh, we need to run task 2. And then task 2 runs for a fixed amount of time, RTOS triggers, run task 1. This is the RTOS tick. A tick list basically says, okay, task run 1 can run, and we set a fixed time that is variable as to when we're going to run the RTOS again. And so this is often very handy for sleeping the processor. So you can say, okay, I'm going to take the processor to sleep for X number of seconds, and then the RTOS will wake it back up. It's also handy if your tasks have to run. Let's say task 2 needs to run in 2 minutes and there's nothing else to be done. Then you can say, okay, let's put everything to sleep for 2 minutes. The RTOS will wake up just before 2 minutes and then call task 2 at the correct time. Now, what is the difference between RTOS and bare metal? Obviously, bare metal can do everything an RTOS does because the RTOS is basically implemented on top of the bare metal. Bare metal implementation is usually faster execution time, uses less resources, power. However, an RTOS generally makes code creation faster. You can develop the code a lot faster, especially when you have multiple developers, because each developer can write their code and not worry about what the other person's code does. An RTOS, however, does not fix bad programming. It amplifies it. If you're a bad programmer and you use an RTOS, it's just going to get worse. It does not solve all the world's problems. It just moves the ball further down the field. If you have a tight development schedule, you might consider an RTOS, especially if you have multiple programmer developers. If your processor is fast enough and has enough flash and SRAM, it's a good choice. With an RTOS, the peripheral drivers are often the hardest part of development because you have to make sure that if multiple tasks use the same peripherals, they're not using the same peripherals at the same time. This has been a presentation on RTOSs as a brief introduction. If you have any other questions, please leave your comments below.